So, a very good morning to all of you in this elective course that is PHY 604 Fundamentals of Semiconductor. And this is a 3-credit course in which we will take around 45 classes, and this is the syllabus of this course in which we will have 3 units. So, first unit is dedicated to about the basics of semiconductor, uh, especially the crystal structure, how the bands form in semiconductor, what is the concept of electron and holes, and how do we get the forbidden gap in semiconductor, what is Fermi level, how does it depend upon the doping concentration, how does the Fermi level depend upon the temperature. Then there is a term quasi-Fermi levels. We will also discuss that. And direct and indirect band semiconductors, wide band semiconductors, degenerate and non-degenerate semiconductors, amorphous semiconductors, magnetic semiconductors, and Hall effect in semiconductors. Then there are the second unit consists of more little bit advanced studies in case of semiconductors, and the last unit covers the growth techniques of semiconductor devices, PN junction diodes, and other type of special purpose diodes like Zener diode, the tunnel diode, Schottky diode, and the bipolar junction transistors or photodiodes, solar cells. So while taking your advanced physics labs, it was felt that you don't have sufficient knowledge of semiconductor. You could not tell the simple answers how the band formation takes place in semiconductor, or how we have the forbidden gap between the valence band and conduction band in case of semiconductor, or how the conductivity of you were asked to plot the conductivity of a semiconductor and a metal as a function of temperature, and almost all of you could not do so. So from that point of view, it is important to understand about semiconductors. Not only that, semiconductors are the materials which are in every device nowadays. You name any device and it will have a chip, integrated circuits, and on that integrated circuits we have so many transistors which are made of semiconductors. You take television, like nowadays we have LED TV or OLED TVs are also coming. You name any device and you find the use in mobile phones. You have a lot of applications of semiconductors. Therefore, in this world, in this time, it is pertinent to know about semiconductors, and it would be beneficial for you to understand about semiconductors from your job point of view, because in coming times lot of industries would be coming in India that would fabricate the semiconductor chips. So if you attend such course, if you know something about semiconductors theoretically, then you have good chance to get jobs in those companies. So this is the syllabus. I will also share with you on email, and there are several textbooks available. Most of you are here, so many of the books will be available in the library, and otherwise all the PDFs are available in the form of PDF on the internet. So I can tell you, for example, this first first book, Asokasap. Its PDF is available. It is available in the library. Then this SMG book is also available in the PDF form uh, on the net. And this Nieman book also, and Streetman Banerjee book also, and the last book, 5 to 6 copies are available in the university library. So you should not find any difficulty in finding these books. If you still have any difficulty, so you can please contact me. I will try to find a solution for that. And besides that, if you find any source that is useful to you uh, as far as this syllabus is concerned, so you are free to read that book or that source. So we start from the very basics about solids. So how do we classify solids? We can classify solids based on many things. How the atoms in solids are arranged, that is one criterion to differentiate among different or various solids. Or there is another criterion like based on conductivity we can also differentiate different type of solids, whether they are conducting or insulators, or their conductivity lies in between them. So first we try to try to classify or try to differentiate the solids based on the arrangement of their constituent atoms. And based on that, we can have two types of solids. One are called as crystalline solids, and the other are known as non-crystalline solids or amorphous solid. So again, the crystalline solid can be of two types. One is the single crystal, and the other one is the polycrystal. And the non-crystalline solids, they are also known by the name amorphous solids, which is a Greek word with meaning without any regular form. So each type of, whether it is a crystalline solid or a non-crystalline solid, each type is characterized by the size of an ordered region within the material. What is an ordered region? It is a region, or it is a volume in which atoms or molecules have a regular geometric arrangement or periodicity. This we have discussed in condensed matter physics course, if you recall. So amorphous, on the other hand, amorphous materials have this order of atoms or molecules only within a few atomic or molecular dimensions. Such solids are formed when the atoms do not get sufficient time to undergo a periodic arrangement. So, and polycrystalline materials have a high degree of order over many atomic or molecular dimensions. On the next slide, it would be clear by when we discuss their image or image. So that would be it would be more clear. These order regions or single crystal regions, they are different in different size in polycrystalline materials, and their orientation with respect to each other is also different. So for example, here we see three diagrams denoted by A, B, and C. In A, you can see the black circles, they represent atoms.
Excuse me,
So,
sir.
yes,
The slide is
Sir,
important.
yes,
slide is not changing, sir.
slide is not changing.
Yes, sir.
Yes, sir.
Okay. So you see only the first slide. Now I think it will change.
Yes, sir.
Earlier it was in the full slide mode. That's why there seems some issue. So I was talking about the classification of solids, and we can differentiate the solids based on whether they are crystalline solids or non-crystalline or amorphous solids. So when we say the solid is crystalline, it means that the arrangement of atoms or molecules in those solids extends up to a very far distance. So this is the meaning of crystallinity, and you have seen this in case of in the condensed matter physics course. But in case of non-crystalline solids or amorphous solids, this regular arrangement of atoms or molecules, it does not extend up to large distances. It breaks up. It is up to, let's say, a nanometer or even smaller length scale. So here we see the three diagrams. The first diagram, in which there are atoms which are denoted by black circles, and you don't see any regular arrangement between the atoms. So for example, we consider this atom. If we move in this direction, we find another atom, we find another atom, but we don't find any other atom here, or we don't find any other atom to its left. So though atomic arrangement is there, but it is in a very small, very small region. Almost we can say that there is, on the whole, there is no periodic arrangement of atoms or molecules, and such solids are known as the amorphous solids. Then we have the polycrystalline materials, in which we can see that there are regions in which we have the periodic arrangement or the regular arrangement of atoms. We can consider any regions. There are 4 regions in this polycrystalline material. This is just to make you understand, but in practical or in actual situation, there are large number of such regions in a polycrystalline materials. So if we consider this lowest region, we see that the atoms are arranged in a particular fashion. If we move any particular distance, so we will find another atom. So that's the meaning of crystallinity. But if we move close to this boundary, then we see that there is interruption in the periodic arrangement of atoms. And after this region, there is another region in which there is periodic arrangement of atoms, but the orientation of these atoms is different in comparison to these atoms. For example, these planes are oriented in this direction, whereas in this region the planes are arranged in this direction. Similarly, in this region also we have periodic arrangement, but the orientation of atom is different. So such materials are known as polycrystalline material. As the name implies, poly means many and crystalline means crystal. So polycrystalline materials are composed of many single crystals, many regions of single crystals. And the region, you can see these lines dividing the regions of different arrangement of atoms or different orientation of atoms. So these regions are divided by the lines. These lines are known as grain boundaries. इन रीजन को जो लाइंस है that separates the two differently oriented regions is known as grain boundary. इसको grain boundary बोलते हैं. Grain boundary is a region where the periodicity of grain interrupts, or periodicity of the grain breaks down. And so the grain boundary is a region of high disorderness. Here the periodicity will break. You can see every region. So, and this region where we have the crystalline arrangement or the periodic arrangement of atoms or molecules, This region is known as grain, and the grains are separated from each other by grain boundary. So please remember that grain boundaries are the regions of highly disorderness. By disorderness, we mean that there is no specific arrangement of atoms at the grain boundaries. Now, if we study any physical properties, for example, conductivity of polycrystalline materials, then the grain will exhibit the smaller conductivity in comparison to grain boundary, because these are the regions of highly disorderness. Therefore, when we look for conductivity, when we want a smaller conductivity, then polycrystalline materials are not good. Other thing you see, because in a polycrystalline materials we have different regions of different orientation. So polycrystalline materials or these amorphous materials, they are isotropic in nature. If you measure their any physical property, for example, electrical conductivity or magnetization, it is same in x direction, it is same in y direction, it is same in any other direction. That's why we say they are isotropic in nature. The last figure, it shows the single crystal lesion. You can see the whole sample or whole specimen of the solid. It contains the regular arrangement of atoms, and all the atoms are oriented in a particular direction. So when we have such very big regions, then the crystal itself is known as single crystal. Single means one and crystal. We have only one crystal. यहाँ पे एक ही क्रिस्टल है, दूसरा कोई क्रिस्टल नहीं है. जैसे इसमें डिफरेंट रीजन्स हैं छोटे छोटे, इसमें पूरे मटेरियल में we have only one region. There is no grain boundary present in case of single crystals, and because the atoms are arranged in a particular direction, that's why the single crystalline materials are anisotropic in nature. And by anisotropy, we mean that they will exhibit different magnitude of physical properties in different directions. It is seen that for single crystals, if we measure the conductivity in AB plane, then it would be different, and if we measure conductivity along the perpendicular direction of AB plane, that is in the C direction, then its conductivity would be different, because whole atoms are arranged in a particular fashion. So far, any question?
Sir, any other property except electrical property?
Can you speak loudly?
Sir, is there any other property except electrical property?
Magnetic properties, optical properties, all are anisotropic in nature for a single crystal.
Thank you, sir.
Okay?
Yes, sir.
So we can compare here the crystalline solids and the non-crystalline solids, that is amorphous solids. As we have said that in a crystalline solids, atoms, ions, molecules are arranged in an ordered repeating pattern throughout the solid. In case of single crystals and in case of polycrystals, there are regions where this periodic arrangement is there. But if we pass from one region to other region through grain boundary, then the periodic arrangement would be there in another grain, but their orientation would be different. Generally, most of the solids are polycrystalline in nature, and it is very difficult to grow single crystalline materials. There are several techniques that we will discuss in due course. known as like Bridgman technique is there to grow single crystal, and we have this Jokralski technique is to grow single crystals. And for semiconductor devices like any transistor or any other device based on semiconductor, we want the material to be single crystal, because if the disorderness is there, if it is a polycrystalline in nature, then it will change its property drastically. For example, if the electron or hole, they are moving in this particular direction, and we want the electron or hole to reach from this region to this region, but they will encounter a grain boundary. They will encounter the grain boundary and they will be scattered in any other direction. That will lead to the enhancement in the resistivity of the material or the decrease in conductivity of the material. Therefore, the device requires that semiconductor should be of the single crystalline nature. So when we say single crystalline in nature, it means that it contains, even if this periodic arrangement can be broken by if we have any foreign impurity, like if we say these atoms belong to silicon, and if you put here any other atom that is different from silicon, then this periodic arrangement will break in that particular region, in the smaller region. So that will also affect the physical properties. So because the crystalline solids are having periodic arrangement, therefore they have the sharp melting points. We can define that. For example, ice will melt at 0 degree centigrade, and but amorphous solids, they don't have very well defined melting points. And isotropism, we have already discussed this isotropic properties, because crystalline solids have the periodic arrangement, especially the single crystals, so they are anisotropic in nature. We measure any physical properties like refractive index, that is optical properties, or electrical conductivity or thermal conductivity, or any magnetic property, they are direction dependent. It means that it will depend upon in which direction we are measuring this property. And isotropic, the amorphous solids, because they don't have any regular arrangement of atoms, that's why they are isotropic in nature. We measure their physical property in any direction, that would be the same. It will not be different. Another thing is the crystalline solids have definite and characteristic heat of fusion. What is characteristic? What is heat of fusion? It is the change in enthalpy when a substance is heated to change its state from solid to liquid. It is more or less closely related to melting points. And the amorphous solids, they don't have the definite heat of fusion. Another interesting property is cleavage property. If we break any single crystalline material, they will have sharp edges. Means they will have very smooth surface if we break a semiconductor, because the atoms are arranged in a particular fashion. So if we break it like this or like this, so the periodicity will be interrupted and we will have very sharp faces. But if we break amorphous solid, there is no periodic arrangement of atoms, so the crack will go randomly. Therefore, they will not have very sharp surfaces, they will have irregular surfaces. There are so many examples of single crystal like silicon, germanium, sodium chloride, diamond, quartz, gallium arsenide, tourmaline, quartz, and all these polymers. For example, polymers are classified as amorphous solids. Rubber, plastic, all these are polymers. So these are few properties by which we can distinguish between crystalline solids and amorphous solids. So that is one criterion based on which we can differentiate among different type of solids. The next one is how the solids transport the electric current from them. So based on this, we can classify the solids. We know the electrical conductors and electrical insulators, and very simple definition is that the solids which allow the electric current to pass through easily, they are known as the conductors, and uh, the materials which do not allow current to pass through them easily, they are known as insulators. And the semiconductor materials are in between the conductors and insulators. Conductors have very high electrical conductivity, whereas the insulators have very poor electrical conductivity, and the conductivity of semiconductors lies in between those of conductors and insulators. So if we want to transport electric current from one place to the other place, then we use conductors, and in order to prevent electric shock from the current flow in conductors, we wrap the conducting wires by insulators. So conductivity is the unit of conductivity. Conductivity is denoted by the symbol sigma, and it has the unit of 1 ohm centimeter or 1 ohm meter, or it is 1 divided by ohm. 1 over ohm is also denoted by Siemens. So it will have Siemens per centimeter or Siemens per meter unit as that of conductivity. And we can do the conductivity measurement on any solid. If we have this solid, and depending upon its conductivity, we can measure its resistance, we can measure its resistance. We connect it with external source of potential V, then current I will flow. A is the cross-sectional area of this semiconductor, and the resistance of this slab would be related to conductivity as 1 over sigma L over A. So now by doing that advanced physics labs, you are aware that conductivity can be measured by conductivity or resistivity can be measured by two methods. One is the two probe and the other one is four probe method. And you must know why the four probe is the accurate method to measure the resistivity of any material, because we eliminate the contact resistance. In case of four probe, we have two separate probes for the measurement of voltage, and two outer probes are used to transport current inside the semiconductor. So in four probe method, the contact resistance is eliminated. But if we have the sample resistance very high, then four probe is not a good method. With the conductivity or resistance of the material can be measured by two probe only. So this is the scale that defines the conductivity of different solids. So for example, here we see we have on the right side copper, aluminum, platinum. All these are examples of metals, and their conductivity is very high, of the order of 10 to the power 6, and it is 1 ohm per meter or Siemens per centimeter. Siemens per centimeter. If we convert it into meters, so it would be 10 to the power 7 to 10 to the power 8. Very, very high conductivity. Then on the left side, we have very poor conductivity, that is from 10 to the power 9 to 10 to the power minus 18 Siemens per centimeter. So the conductivity is very, very poor. And these are examples: glass, fused silica, wood, polymers. All these are examples of insulators. So, by the way, polymers were considered to be insulators up till 2000, but in 2000, chemistry Nobel Prize was given to three scientists. Two were from Japan and one was from America. They made polymer as conducting. So now we have a branch of research in which we study conducting polymers. So now polymers are not only insulating, but they are conducting as well. And in between insulators and conductors, you see there is a large region. There is a large region that belongs to semiconductor. That's why we say them as, or we call them as semiconductors, because their conductivity is between those of metals and metals and insulators. Now, why semiconductors are very important? The answer is, in case of conductors, the number of free electrons is fixed. Can anybody tell me what is the order of concentration of electrons in conductors?
10 to the power 28 per meter cube.
Yes, 10 to the power 28 per meter cube. So it will not change. It will not change. It will remain fixed. In case of insulators, it is very, very small, up to 10 to the power 4, 10 to the power 5 per centimeter cube. Very, very small. It is also not going to change. That's why the conductivity of metal is fixed at particular temperature. Conductivity of insulators is also fixed at particular temperature. But if we consider any semiconductor, its conductivity can be changed. If we slightly substitute. For example, if 10 to the power 9 silicon atoms, 10 to the power 9 silicon atoms are replaced by just one arsenic or phosphorus atom, its conductivity will change significantly. Therefore, we can play with the conductivity of semiconductor, and we can have the material with desired conductivity. That's why the semiconductors are so important for devices. That is one reason. The other reason is the metals, they do not possess any band gap. In metals, the valence band and conduction band overlap with each other. There is no band gap. In case of insulators, the band gap is very, very high, not useful for ambient conditions. But in case of semiconductor, for example, silicon, the band gap lies in the visible region. Therefore, we can utilize these semiconductors to fabricate the solar cells, or to fabricate another optoelectronic devices. So silicon is one of the prominent semiconductor, and the reasons for this is I will tell you shortly. Other semiconductors are like gallium arsenide. It is used for optoelectronic devices. Optoelectronic devices like light emitting diode, semiconductor laser, or you can have other optoelectronic devices also, but the prominent ones are light emitting diodes and semiconductor lasers. So this is the resistivity graph of insulators, conductors, and semiconductors. It is just the inverse of that, and you can see that in the semiconductor region we have We have germanium, silicon, gallium arsenide, gallium phosphide, cadmium sulfide. So many semiconductors we can have, and all these are examples of conductors, whereas glass, nickel oxide, diamond, sulfur, fused quartz, all these are examples of insulators. They have very high electrical resistivity. On the top side we have electrical resistivity, on the bottom side denotes the electrical conductivity. So as I told you that semiconductor materials are very useful for electronic devices because their electrical conductivity can be greatly influenced by the introduction of small number of impurities. And not only that, their conductivity can be influenced by the application of either electric field or magnetic field, or light or temperature. There are several perturbations that can be applied to semiconductors to change their electrical behavior. So we have already discussed this, that semiconductors used in the integrated circuits, they are single crystalline in nature. And single crystalline means if we have one unit cell like this, then we need to repeat it in all three dimensions, and there should not be any break. There should not be any break in this periodic arrangement. Then we will get a single crystal. So here these circles, these spheres, they represent the atoms, and these sticks, they represent the bond between two silicon atoms. Generally, most of the semiconductors, they crystallize in the diamond structure. So in diamond structure, you know that each atom is covalently bonded with four neighboring atoms, and each of these covalent bond consists of two electrons. So this is a covalent bond. It is strong. And it provides, or it gives the stable crystal structure. So if you recall the condensed matter physics discussion, then we discussed the diamond structure in detail, in which we have it is. Can anybody tell me what is the crystal structure of diamond? What is the crystal structure of diamond? Is it tetragonal, orthorhombic, BCC, FCC, simple cubic? What it is? Hello? Are you there? If you are
Yes,
unable,
sir.
if you are unable to tell, just tell me. I will
Yes,
tell
sir.
you. So it is FCC structure, two interpenetrating FCC structure. One FCC structure has atoms at the corner and atoms at the center of each face, and the other FCC structure will consist of atoms that is quarter and quarter position. So this is another atom here that is located at 1 by 4, 1 by 4, 1 by 4 position. So two atoms you will have 1 by 4 and 1 by 4 position like this, and two atoms you will have at 3 by 4, 3 by 4 position there. So these are two interpenetrating FCC lattices which are shifted from each other by quarter and quarter position. So silicon, germanium, all these semiconductors, they crystallize in this diamond structure. And another similar structure is the zinc blende structure, in which though the structure belongs to diamond, but we have different atoms. For example, gallium arsenide semiconductor, very useful semiconductor, in which, because we have two different type of atoms. One is gallium and the other one is arsenic. So the arsenic atoms sit at the corner of the unit cell and at the face center of this unit cell, whereas the gallium atoms, they sit at the diagonal position. You can see these are the body diagonal positions. So these two gallium atoms, they sit at 1/4, 1/4, and 1/4 position, whereas remaining two gallium atoms, they sit at 3/4, 3/4, and 3/4 positions. So when we have all atoms similar, it is diamond structure, and when we have different atoms, it becomes the zinc blende structure. So gallium arsenide is an example of a uh, zinc blende structure. Or you have another semiconductor, that is zinc sulfide, uh, that also has this zinc blende structure. So now, as I told you, semiconductors, we have silicon, germanium, gallium arsenide. All these are examples of semiconductors. And as we proceed further, we will come to know about other type of semiconductors. But for the time being, we give three examples: silicon, germanium, and gallium arsenide. Up to up to 1950s and 1960s, because the first transistor was made in 1948. So you can say in 1950s and 60s, germanium was the major semiconducting materials that was used in electronic device. But later, silicon replaced germanium in all the semiconducting devices, and now we don't use germanium. The reason is, there are several reasons for that. One is, silicon is present in abundance in the form of silica or silicates on earth. So it is abundant in nature, easily available, economically it is easy to grow in the form of single crystals. And the second problem with germanium is that of leakage current, the current due to minority carriers. And for electronic devices, this is a big problem. If we have the devices made of germanium, so, and if we increase the temperature of the device, so the leakage current becomes twice with every 7-degree rise in temperature for germanium device. But if we consider, if we take silicon, then for silicon devices, if we raise their temperature, the leakage current would become double with every 10-degree rise in temperature. Therefore, the silicon devices are better than that of germanium devices, and it was the reason why silicon replaced germanium in all the electronic devices. I hope it is clear to you. So far so good. So in this periodic table, we have several columns: column second, third, fourth, fifth, and sixth. And the reason to show this table is that we have elements from group 4 that are used to make semiconductor. For example, silicon and germanium, they are very much used, but carbon is not used. Carbon is not a semiconductor. Carbon is an insulator. Of course, in different forms it can be conducting also, but elemental carbon is insulator in nature. It is not used for semiconductor. And if we dope any, you know that if we dope any element from group 3rd in silicon or germanium, then we can make it a p-type semiconductor. Or if we dope any element from group 5th, then we can make it p-type semiconductor. Not only that, we can also have semiconductor like this. If we choose zinc from group 2nd and oxygen from group 6, then it makes zinc oxide, and it is a very useful semiconductor. Zinc oxide, many devices are made based on zinc oxide semiconductor. A lot of research has been done on zinc oxide semiconductor, but it is very difficult to grow p-type semiconductor because of oxygen vacancies. Originally it becomes n-type semiconductor, and therefore it is very difficult to make p-type semiconductor. But nevertheless, to fabricate zinc oxide thin films is very, very easy. We can have another semiconductor, cadmium sulfide, cadmium telluride, cadmium selenide, all based on mercury. So we can have one element from group second and another element from group 6. Then that can also be used to make a semiconductor. Or we can have we can have an element from group third and another element from uh, group fifth. Then we can also make a semiconductor. So for example, in order to make gallium arsenide, we choose gallium from group third and arsenic from group fifth. It will make gallium arsenide very useful semiconductor. Or we can have indium from group third, arsenic from group fifth. Indium arsenide is also is a very good semiconductor. Aluminium nitride, aluminium phosphide, gallium phosphide. Like this, we can have so many semiconductors if we choose the elements appropriately. So we know that the silicon and germanium, they are known as elemental semiconductors. Elemental semiconductor means the semiconductor is composed of only single atoms. Silicon में silicon के अलावा तो और कुछ होता नहीं है. If we consider a very pure single crystal of silicon, then it will have only silicon, no other element. Or germanium, the same thing. That's why these are known as elemental semiconductors. But we can also have compound semiconductors in which we have more than one element present. So compound semiconductors are like binary compounds, ternary compounds, and quaternary compounds. So binary, as the name implies, binary means two. So it will have two elements. Ternary means three, so it will be made of three elements, and quaternary means it will be made of four elements. So, for example, this semiconductor, aluminium X, gallium 1 minus X, uh, arsenic. So we have gallium arsenide semiconductor, but in which part of gallium is replaced by aluminium. Aluminium and gallium, they are in the group third. So this becomes a ternary semiconductor. And we can also have quaternary semiconductors. So for example, if arsenic is replaced, so part of arsenic is replaced by phosphorus, so it will become a quaternary semiconductor with four elements: gallium X, indium 1 minus X, arsenic Y, P 1 minus Y. And all these semiconductors are used to make heterojunction devices. We will sometime discuss about the homojunction and heterojunction devices. In case of optoelectronic devices, the heterojunction devices are more useful because they are more efficient in comparison to the homojunction devices. Heterojunction means that across the device we will have different band gaps in different regions. So compared with the element semiconductors, the preparation of compound semiconductors in the form of single crystals, it involves very complex processes. It is not very easy to grow. Even binary semiconductor, it is not very easy to grow. Gallium arsenide, gallium nitride, gallium phosphide, all these are useful semiconductors, and the molecular beam epitaxy is is a technique that is used to grow all these semiconductors in very pure form, so that they don't have any other impurities. But that molecular beam epitaxy, or abbreviated as MBE, it is a very costly technique, not available everywhere. So many of the compound semiconductors, be it binary, ternary, or quaternary semiconductors, they have electrical and optical properties that are quite different